Abhiyanta Siksha is launched with a motto to impart an experiential understanding of technical education. The course outcomes are: equips junior engineers to solve real-time industry problems, prepares graduates for competitive exams, supports engineering students in their graduation studies, benefits diploma and high school students in engineering sciences. Problems are explained, solved, and supplemented with hands-on practice for students. Welcome to the online course Abhiyanta Siksha. The topic that we are covering in this course is engineering mechanics with subtopic friction. Let's recall Newton's laws of motion. The first law: if the resultant force acting on a particle is zero, the particle will remain in the same state until and unless compelled by the external force. The first law embodies the principle of force equilibrium, which is the primary focus in the study of statics. The second law: if the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of the resultant and in the direction of this resultant force. F is equal to ma. The second law is the basis for the most of the analysis in dynamics. Third law: the forces of action and reaction between the bodies in contact have the same magnitude and the same line of action and opposite sense. When the resultant of all the forces acting on a particle is zero, the particle is in equilibrium. Third law is the basis for understanding of force, and force always occurs in pairs of equal and opposite forces. So let us understand what is angle of friction. Now, imagine a body is resting on a ground surface. This body, and this is ground, has a weight W, and this body is now being pulled with an external force P. For this, to understand the forces that are exerting on this body, let us draw first free body diagram. So what is a free body diagram? An isolated view of the body considering only the external forces exerted on the body is called free body diagram. So if this is the body, let us see what are the forces that are acting on the body. So this body, the weight acts in this line, and let the force be in this line. Then what about the contact forces that are acting at this zone? To understand this, let us have a clarity on the mechanisms of friction. Now you look at the body and the ground. We know that no body is absolutely smooth. There are certain amount of roughness exists on the surface of every body. So let us imagine this particular crests and peaks is the roughness underneath the body, and this crests and peaks are the roughness of the ground. Now once both are in contact with each other, you are applying the force P. The roughness will make us consider two components of forces at the contact. One is normal, let me say N1, and the other one is frictional F1. Similarly, N2, F2, N3, F3, N4, F4, where F1, F2, F3 are frictional resistance, and frictional resistance is always a self-adjusting force. N1, N2, N3 are the normal reactions done by the ground onto the body, and they are always perpendicular to the surface. Perpendicular to the surface. So, the resultant of that I can represent as a reaction force vertically upwards and on the same line of action where the weight is acting. And the resultant of all these F1, F2, F3, F4, I can represent it as F at the contact surface in a direction opposite to the applied force. Now, the body starts impending motion once this F reaches to F max. That is what is called limiting friction. So, this is the representation of a free body diagram of the body and the ground system. Next, this let me say one representation. There is another way of representing the same system, that is with resultant force. Now, you can replace F1 and N1 with frictional resultant force R1, which is at an angle of phi. Similarly, another resultant R2 at an angle of phi 2, R3 phi 3, R4 phi 4. So, what are R1, R2, R3, R4? They are the resultant forces for N1, F1 or N2, F2, N3, F3, N4, F4. So, combinedly, I can represent now the same system with W as a weight and applied force in horizontal direction, and the resultant R making an angle phi with the vertical. So, you can replace F max and N with R and phi. So, this is another way of representing. Now, let us derive what is angle of friction. Now, I can resolve this R as two components, which are R cos phi and R sin phi, right. Now, if I consider in the direction sigma Fx equal to 0, then my F max is equal to R sin phi x max. Similarly, in the y direction, if I consider N is equal to R cos phi. Let me say this equation 1, this as equation 2. Now, divide this equation 1 with equation 2, that is F max by N equal to R sin phi by R cos phi. That is, let us assume that mu, that is coefficient of friction, is equal to the ratio of maximum limiting friction divided by the normal reaction exerted by the ground on the body. So, I say mu is equal to tan phi, because the ratio of sin phi by cos phi is tan phi. So, phi is the angle of friction and mu is the coefficient of friction. So, you remember this relation and the angle of friction. Types of friction problems. The first step in solving a friction problem is to identify its type. In the first type of problem, the condition of impending motion is known to exist. F max is equal to mu s into n. The equations of equilibrium will hold good. That is sigma f phi is equal to 0, sigma f x equal to 0 and sigma m equal to 0. In the second type of problem, neither the condition of impending motion nor the condition of motion is known to exist. Now, to determine the actual friction conditions, we first assume static equilibrium and then solve for the friction force F necessary for equilibrium. The three outcomes are possible for this. The first one is F is, that is the frictional force is less than maximum frictional force, that is the limiting frictional force. Here, the frictional force necessary for equilibrium can be supported and therefore the body is in static equilibrium as assumed. So, we emphasize that the actual friction force F is less than the limiting value F max and that F is determined by the equations of equilibrium. The second condition is F is equal to F max. Since the friction force F is at its maximum value F max, motion impends. The assumption of static equilibrium is valid. F is greater than F max. This condition is impossible because the surfaces cannot support more force than the maximum mu s n. The assumption of equilibrium is therefore invalid and the motion occurs. The friction force F is equal to mu k into n. In the third type of problems, relative motion is known to exist between the contact surfaces and thus the kinetic coefficient of friction clearly applies. Now, let us understand the fundamentals of friction with a numerical problem, a simple problem. Consider a block of 40 newtons weight acting on a horizontal table. Then an applied force is acting on the block in horizontal direction with a magnitude of 20 newtons. Now, the weight 40 newtons causes a normal reaction in upward direction. This is the force caused by the table on the block. Now, since you are moving this block, trying to move the block with an external force 20 Newton, a frictional resistance occurs at the contact surface of the block and the table and in the direction opposite to the applied force, that is towards left. Now, the question is, if the block does not move on the table, how much frictional force the table is applying on the block? That means, in other words, calculate the coefficient of friction considering G as 10 meter per second square. Now, since the block is at rest, apply the equilibrium conditions, that is sigma fx equal to 0 in this case. That means Fs is equal to 20. This one. What is Fs? It is nothing but the frictional resistance offered by the table on the block. Now, since the block is not moving, your Fs is less than mu into n. What is n? N is a normal reaction by the table on the block. How do you obtain that? Use another equilibrium condition, Fy equal to 0, the sum of the forces in y direction is 0, that is 40 equal to n is 40 newtons. Now coming back, if Fs is less than mu n, that means mu is greater than Fs by n, that is nothing but 20 by 40, which is 0.5. So, frictional resistance of 0.5 is acting at the contact surface of the block and the table. Now, let us understand angle of repose. Angle of repose is something that is connected to inclined surfaces. Now, imagine a body is kept on an inclined surface. It's a body, and the angle of inclination is theta. This is the ground and this is the body. Now, when theta is 0, the surface is horizontal and the body does not move. Now, as you increase the theta value, at a certain value of theta, the body just starts moving. That is, motion is impending. Now, that angle at which the body starts moving is called angle of repose. Now, let us derive the value of this angle of repose. Now, the body has a weight W, which always acts perpendicular to the ground surface. This is the ground surface, right? Now, let us represent the other forces that are acting on the body. Now, let me say first, because the body is moving downwards, obviously the frictional force is in an opposite direction to the motion, that is in upward direction, F max, right? Then there is a normal reaction acting on the body by the inclined surface, that is this surface, right, which is again perpendicular to the inclined surface. Now, here there are two surfaces shown in the figure. One is the ground surface, the other one is the inclined surface. Now, let me call ground surface as x dash and inclined surface as x double dash and x triple dash. Okay. Now, if I take the y axis of this becomes y dash and this becomes y double dash and y triple dash. Okay. So, there are two axes here. Let us resolve all the forces on one axis. For example, I shall consider the x double dash x triple dash as the axis for all the forces to represent. See, this is the inclination x double dash when x triple dash, and I draw a normal which is y double dash and y triple dash. Now, on this, the W is the weight of the object is acting at an angle of theta, say theta, with respect to y double dash and y triple dash. So, represent that angle of W here at an angle of theta. Whereas n is already lying on the y-axis. So, I represent n here along y double dash, y triple dash. Then you have force, frictional force F max lying on the x-axis directly. So, the only force among the three forces, that is W, is inclined to an angle of theta to the vertical y double dash and y triple dash. So, let us resolve this force onto this y-axis and x-axis. Since this is theta, we get this as W cos theta and this as W sin theta. Right. Then I consider the conditions of equilibrium here as sigma F x double dash x triple dash equal to 0. Then I get as F max equal to W sin theta. Let me call this as equation 1. Then you have sigma F y double dash y triple dash equal to 0. Here this downward force is equal to upward force, that is n equal to W cos theta. Right? Now, let us divide equation 1 by equation 2. We get F max divided by n equal to tan theta. We already know that mu, which is equal to F max by n by assumption, is equal to tan phi. So, I represent tan phi in the place of F max by n and say tan phi equal to tan theta or phi equal to theta, where phi is said to be angle of repose. So, when the friction angle of repose is equal to the angle of inclination, the body starts its impending motion. So, this is what is called angle of repose. There is another way of representing the free body diagram with respect to R. That is, you can draw the inclined surface, okay, and the line of action of force where W is acting. W always acts perpendicular to the ground surface, remember. Okay. Then the resultant of this acts as a collinear force on the same line of action at an angle of phi. At an angle of phi. Okay. So, this is another way of representing the resultant force, replacing F max and n for the problem. 4 different situations may occur when a rigid body is in contact with the horizontal surface. Let us understand case by case. In the first case, the P applied force is acting in the vertical direction. So, there is no friction between the contact surfaces. Hence, Px, that is the resolved component of P in x direction, is 0 and frictional force is also 0. Coming to the second case, in this case, the P is pushing the body towards the right direction. The P applied at a smaller angle with the horizontal line. Now, when the P is resolved, the resolved components Px and Py will contribute to the different actions. The Px contributes in moving the body towards right direction, and Py does not contribute for the motion of the body. Now this Px is having an opposite reaction force from frictional effect, that is F. So if the Px is less than Fm, then there is no motion causing in the body. So there is no evidence that the maximum frictional force has been reached. F is not equal to Fm, which is equal to mu s into n. Now in the third case, if you just increase the angle or change the angle, for that matter, change the angle of application of force with respect to the horizontal line, then the motion may impede when Px is equal to Fm. If the body just about to slide, then F is equal to Fm is equal to mu s n may be used. In the fourth motion, that is, if the angle of application of force with respect to the horizontal line is again changed, slightly increased, then there can be a motion when Px is greater than Fm, or otherwise Fm is equal to mu k into n. Now let us understand the same phenomenon with respect to the resultant force R. That means we are replacing the F max and n with R. In the first case, there is no friction, and you notice that the resultant force R is equal to n. In the second case, there is a resultant force R which is at an angle of phi with respect to the normal reaction, and there is no motion. Therefore tan phi s is equal to Fm by n, which is equal to mu s n by n, that is equal to mu s. In the third case, where the motion just starts impending, then the fourth case, there is a kinetic friction occurring at the surface. So tan phi k is equal to Fk by n, which is equal to mu k n by n is equal to mu k. Then in the next situation, where we consider the inclined planes. In the first case, if you see the horizontal surface where theta is equal to 0, so there is no friction and theta equal to 0. In the second case, where the horizontal surface is inclined to an angle of theta, and if this theta is less than phi s, then your resolved components n is equal to w cos theta and f is equal to w sin theta, and if this phi is less than phi s, there is no motion in the body. Coming to the third case, where theta is equal to phi s, that means you increase the theta such a angle that the body just starts sliding. That is called motion is impending. In that situation, your R and W are collinear. Both the line of action of forces lie on the same line. Then comes the fourth case, where the theta is greater than phi s. The resolved components n is equal to w cos theta and f max is equal to fm. So if n tan theta is greater than n tan phi, w sin theta is greater than f max, then f is equal to mu k n, phi is equal to phi k, that is equal to less than phi s, which is less than theta. R is not vertical. Forces acting on block are unbalanced motion. Now let's start solving some problems. The question here is, there is an object placed on an inclined surface which is having an inclination of 30 degrees from the ground surface. The weight of the object is 200 newtons and the ground surface has a friction of 0.3. Now a 300 Newton force externally applied on the object so as to resist the sliding motion of the body. Now the question is 300 Newton sufficient to stop the sliding of the body on the inclined surface at an inclination of 30 degrees? So let us check through the problem if this 300 Newton is adequate enough to hold the body on the inclined surface. For any problem in engineering mechanics, there are 5 major steps to be followed. Step 1 is understand the problem. 2. Sketch free body diagram. 3. Resolve the forces. 4. Apply equilibrium conditions. And 5. Solve the simultaneous algebraic equations and understand the result. So in short, I can say understand, sketch, resolve, apply, solve. This is applicable to all problems of engineering mechanics. Now, the second step, that is sketch the free body diagram. I can draw the free body diagram for this on inclined surface. Let me say xx dash and y dash. So the W is the force placed here. Obviously, this makes an angle of 30 degrees with the y dash plane. Then you have a 300 Newton acting at same 30 degrees to the plane surface parallel to the inclined surface. So you have a 300 Newton force acting at an angle of 30 degrees with this. Now, if you imagine the body is sliding down, your frictional force acts opposite to the sliding motion, that is in upward motion, that is F. Then you have a normal reaction that is perpendicular to the inclined surface, which occurs at this position. The weight of the compound body is 200 newtons. Agreed. Now you have 4 forces here. One is the weight, the other one is the reaction, then you have applied force, and then frictional force. Let us first resolve the forces onto the x and y axis. So this is 30 degrees with this. Obviously, this becomes W cos 30, and this component is W sin 30. Now when this is 300 inclined at 30 degrees to the x axis, so this becomes 300 cos 30, and this becomes 300 sin 30. So now we have resolved both the forces, and all the forces are now on along x axis and y axis. Let us now assume the forces that are shown in this direction are positive and the forces that are shown in this direction are negative. Similarly, forces that are shown in upward direction in y-axis are positive. Forces that are shown downward direction on y-axis are negative. Sign convention. Then we have finished first understanding sketch, then was resolve forces we have completed. Next one is apply equilibrium conditions. Applying equilibrium condition, first one is sigma fx equal to 0. In sigma fx equal to 0, what are the forces that are acting on x-axis? F, w sin theta, 300 cos theta. So, F in that direction is positive, F positive, W minus W sin 30 because this is negative direction. This is again positive direction plus 300 cos 30 equal to 0. Let me call it as equation 1. Since I know W as 200 Newton, substitute that value, get F as around 160 Newtons. So, for the balance to exist, the frictional resistance here is 160 Newton required. Now, you should know what is the actual resistance existing at the contact surface, which is more or less the depending on mu of the contact surface. Now, to get that, what you do here is you take the next equilibrium condition sigma Fy equal to 0. In sigma Fy equal to 0, look at the forces acting on y-axis. One is W cos 30, 300 sin 30 and N. Now, follow the sign convention. Forces acting in upward direction, that is N positive, and downward direction W cos 30 and 300 sin 30 negative, minus W cos 30 minus 300 sin 30 equal to 0. Now, again substitute W as 200, you get solved for N, it is coming around 323 Newtons. 323 Newtons. Now, let us calculate the limiting friction. Limiting friction F max is equal to mu into N. Given mu as 0.3, N as 323, coming around 97 Newtons. Around 97 Newtons. So, here the maximum limiting friction is 97 Newtons, whereas the required one is 160 Newtons. So, F is greater than F max. That means the body will not slide and the 300 Newton is adequate enough to balance the body on the inclined surface without sliding down. So, before we go to the next problem, let me explain some fundamentals about moment of force. So, the moment of force is the turning effect of a force, and it is mathematically represented as force multiplied by the distance from axis. So, the mathematical expression for moment is F into D. F into D. Now, here I am teaching you in a scalar method and not in vector method. We can deal vector method at later stage. Now, let me explain you with some cases. Now, this is one particular case where a rod of length L is fixed at one end and a force F is acting on the free end. The rod length is of L. Now, in this case, how do you calculate the moment caused by the force F? The free body diagram for this could be, since it is fixed on both sides, on it can be written as RAX and RAY as reactions. And F is the force acting at a length of L. So, let us calculate the moment occurred at A due to F. The force vector, the direction of the arrow is in downward direction. So, you can consider clockwise effect as positive and counterclockwise effect as negative in all our calculations. So, to calculate the moment about A by the force F, you hold the force F here and rotate the force towards A. That means it has to move this way. That means the moment about A is, as I said, product of force and distance. The force is F multiplied by the distance is L. The next immediate thing is the sign convention. As I said, if the moment is clockwise, consider it as positive. So, this is a clockwise movement. Therefore, this becomes positive. Now, let us consider this particular case. In this case, the force is acting upward direction, and again you have the constraint here which creates the reactions RAX and RAY with L span length. Now, this time you have to take the moment about A by rotating the force towards the constraint, that means this direction. Therefore, MA is again F into L, however, it is in anti-clockwise direction, so the sign convention becomes minus. Now, let us take another case where you have more forces and more constraints. Now, this is a rod, AB is a rod fixed at one point A and hinged at another point B. Now, there are two forces acting on the rod, F1 which is inclined at an angle of 30 degrees and is a distance of L1 span length from A. Another force F2 acting vertically downward direction at point D. The total span length is L and the points of force are located at L1, L2 and L3. Now, let us calculate the resultant moment for this system. For this, you draw the free body diagram as again the reactions acting here are RAX, RAY, okay, and this is a hinge. A hinge again has RBY and RBX. Now, this force has to be resolved to x component and y component. So, let me mark point C, point D, and point C F1 is now resolved to F1 cos 30 and F1 sin 30. The next force is F2 here. Now, let me explain you the moments both at A and B. Now, suppose if I take moment about A, that means sigma MA equal to 0. I am taking moment about A. Now, what are the forces that contribute to the moment about A here? F1 cos theta 30 degrees does not cause any movement about A because it is lying on the same line. That means there is no perpendicular distance to cause the movement. So, this does not cause any movement. Then F1 sin 30, yes, it contributes to this movement here. F2 contributes to the movement. RBX does not contribute because again it is lying on the same line of axis, but RBY contributes to the movement here. So, you have three forces that contribute to the movement about A. Now, step by step let us see. F1 sin 30, if I rotate F1 sin 30 force vector towards A, this way. So, I get F1 sin 30 multiplied by L1. Since it is clockwise, I put positive. The next one is F2 rotated towards the constraint A is again clockwise. So, plus F2 into L1 plus L2. Then you have RBY rotated towards A, which is anti-clockwise. So, minus RBY multiplied by total length L, that equal to 0. So, if you know F1, F2, L1, L2, L3, you can calculate RBY from this relation. That is the reaction at B, that is a hinge reaction in vertical direction. Now, let us take movement about B this time. Let us take movement about B. That means sigma MB equal to 0. So, when you are taking movement about B, let us understand what are the forces that again cause for the contribution. RAY can give movement, but RAX does not give movement. F1 sin 30 can give movement, F2 can give movement, but RBY cannot give again, and RBX and RBY both cannot give because you are taking that is a movement center. Now, taking movement about B now, let us start with RAY. Now, RAY, which is vertically upwards, has to rotate about B. So, when I am rotating about B, the movement here is, let me mark in a different color, movement here is clockwise, right. So, clockwise RAY multiplied by L plus. Now, this time F sin 30 is rotating in the other direction, this direction. That means minus F1 sin 30 into L minus L1 or L2 plus L3. Then F2 rotated in towards the movement center B is again counterclockwise. So, F2 multiplied by L3 is equal to 0. So, having known the values of F1, L, L1, L2, L3, you can calculate RAY from this relation. So, if you have the clarity about the movement centers and the distances that has to be considered to calculate the movement of force, then we can solve some more problems in this direction. Let us start problem number 2. Now, in this problem, there is a bar of length 10 meters placed on the two rough inclined surfaces. The weights 100 Newton and 200 Newton are acting on the bar, and the bar is negligible weight. It has a negligible weight. Now, let us draw a free body diagram for this system. Now, this is 100 Newtons and this is 200 Newtons. So, the higher weight is on this side. Now, because the weight is more here, the bar tends to move downwards, and here it tries to move upwards. Okay. So, based on this motion, we can represent the frictional force direction. Now, let us first draw the free body diagram for the figure. The free body diagram goes as the bar, okay, the rough surface this way and this way, the forces 100 and around 200 at a distance of x from one surface, at a distance of 2 meters from here, and the total span length is 10 meters. Right. Now, the inclined surface will exert a reaction on the bar, which is, as I always said, perpendicular to the surface. I call it as NA. Now, the angle of this is 30 degrees. So, when this is 30, this becomes 60. Okay, this becomes 60. Then, as I explained, because the body here moves down and here moves up, the resistance, frictional resistance will tend to move downwards. Therefore, the frictional resistance, that is FA, if I call, is in downward direction. Right. Now, let me draw one horizontal and vertical line so as to know its position on the x and y axis. Let me call this as x axis and this as y axis in our problem. So, if this is 60, then this could be 30. This could be 30. Similarly, look at this. The reaction here, the same exercise, but NB, and this angle is 60, therefore, this angle is 30. Since the body is moving here downwards, your frictional resistance is upwards. Okay. So, I can draw another axis for this as 60 with the horizontal. Now, let us resolve the forces that we are representing here. If NA cos this thing, then you have this as NA cos 60 and this as NA sin 60. FA is in downward direction. So, this is FA cos 30 and this is FA sin 30. Now, if it is NB, then your resolved component NB cos 30 and NB sin 30. FA in that direction gives you FA cos 60 and FA sin 60. So, now let us apply equilibrium conditions, that is sigma Fx equal to 0. So, what are the forces that are acting in x direction? This one, and this one. So, mark x in this direction is positive, in this direction is negative. Then you have FA cos 30 positive plus NA sin 60, because it is also towards right, minus plus FA cos 60 minus NB sin 30 equal to 0. Call me as 1. Here FA is equal to mu into NA. Mu happen to be same here and here. Okay, if there are two different surfaces, like one is metal surface, the other one is earth ground, then mu values would be different. Now, next equilibrium is Fy equal to 0. So, let us see the forces acting in y direction. Let me say this and this. Now, y in upward direction is positive and downward direction negative. So, look at let us start from here. It is in downward direction. So, minus Fa sin 30 upward direction plus Na cos 60, this one minus 100 minus 200 plus Fa sin 60 plus Nb cos 30 equal to 0. Equation number 2. Now, your Fb is equal to mu into Nb. If you have, oh, I am sorry, this should be represented as B and this is also B, right. So, this becomes Fb. B. So, Fb is mu Nb, Fa is mu Na. Okay. Now, these two are not sufficient for us to get the value of x. The question is, how much is x? Not possible to calculate x from the two equations. So, you need to go to the third equilibrium condition, that is sigma m equal to 0. So, the moment occurs both at A as well as at B, that is sliding, right. So, the moment occurs at both the places. So, it is your choice to select which point has to be considered for the equilibrium equation. So, let me consider A for moment, Ma equal to 0. So, if I have to take moment about A, that is this point, let me see what are the forces that are actually contributing to the movement about A. So, if these forces cannot contribute as they are on the same axis, these forces cannot contribute. They cannot contribute because they are all lying at this same axis of moment center. But you look at 100, yes, this contributes, 200 contributes, Fb sin 60 contributes, Fb cos 60 contributes, Nb sin 30 contributes, Nb cos 30 contributes. So, 1, 2, 3, 4, 5, 6, all 6 forces can contribute to the movement about A. So, step by step, let us put down those values of movement. As we said, movement is force into distance from the axis. Now, this is the force, this is the moment center. So, rotate the force which is in vertically downward direction towards the moment center this way. So, here in movement again, let me recall, clockwise is positive, counterclockwise is negative. So, here this is clockwise, I call it positive, where force here is 100 multiplied by the distance here is 2, 100 into 2. So, the next force that contributes to the movement is 200, which is vertically downward direction. So, 200 taking movement about A in this direction, rotate it in this direction, which is a clockwise direction. And the distance from the moment center is 10 minus x. 10 minus x. So, the moment value is force 200 into 10 minus x. Then comes your FB sin 60. FB sin 60 having in vertically upward direction, looking at the moment center in this direction. So, that goes in counterclockwise direction, minus FB sin 60 multiplied by the distance, that is nothing but the span length, into 10. Then your FB cos 60 cannot contribute to the moment because it is lying on the same axis. Similarly, your NB sin 30 cannot contribute because it is lying on the same axis. Then your NB cos 30 here will contribute to the moment in moving in counterclockwise direction, that is minus NB cos 30 multiplied by 10. That is equal to 0. So, this is the equation number 3. So, if you solve the unknowns FB and NB from these equations and substitute them here to get x. So, all the 3 algebraic equations are solved and the unknown is calculated. Now, the x here becomes around 3.01 meters after calculation. So, this distance from here is around 3 meters from the rough inclined surface. Let us start the next problem, problem number 3. There are 3 blocks A, B, C of different weights and different materials placed on an inclined surface which is having an inclination of 20 degrees with the horizontal surface. Now, the mass of block A is 60 kg, the mass of block B is 40 kg, the mass of block C is 20 kg. Let us assume the gravitational acceleration due to gravity as 10 meter per second square. Now, the coefficient of friction in static and kinetic conditions for A and C are 0.5 and 0.4, and coefficient of friction for static and kinetic are 0.3 and 0.2 for B. That means that A and C are say one material and B is a different material, because the surface is common to both. That is the reason you have different coefficient of frictions. Now, the question is, does the 3 blocks slide down at this particular angle of inclination? That there is no external force acting on it, only based on the gravity or self weight of the bodies. We should check if the bodies will slide down the inclined surface. Let us start with body C. The body C, will draw the free body diagram for body C. The free body diagram of body C goes this way. Normal. The weight always is perpendicular to the ground surface. Okay, do not draw the ground surface here. This is WC, which is MC into G. Okay. If this is 20 degrees, so this is 20 degrees and this is NC. You resolve this to weight component MCG cos 20 and MCG sin 20. Now, let us assume that it is sliding down, then the frictional resistance will be in upward direction, calling it as FC. Okay. Now, Apply the equilibrium condition in y direction, Fy equal to 0. So, the sum of the forces acting upward and downward equal to 0. So, Nc minus Mcg cos 20 equal to 0 is the one expression where you can calculate Nc. Now, check if the block C is sliding or not. That is the first question. To check that, you have to calculate the frictional resistance offered by the body on the inclined surface, that is, calculate this value. That value is, you can say, sigma fx equal to 0, where Fc is equal to mcg sin 20. Substitute the value of Cg20, that is 20 into 10 into sin 20. After this, you have to find the frictional force that resists the motion in downward direction. That is mgc sin 20. So, if you calculate mcg sin 20, substituting these values mc20, g10 sin 20, you are getting around 68.4 newtons. Now, you have to calculate the available frictional resistance at the contact surface. The available frictional resistance at the contact surface here is obtained from the expression mu c into ns. Mu s into ns from equation 1 can be considered as 20. Mu s for block C 0.5 into mc20 into 10 into cos 20, giving you around some 93.7 newtons or so. So, since this available frictional resistance is higher than the frictional resistance offered, so Fc is greater than the downward motion, the body will not slide. Body C will not slide. So, the next body, let us calculate for A. For body A, you need to do the same exercise. Body A, this is MAG, NA, 20 degrees here. So, calculate MAG with this as 20 degrees, MAG cos 20, MAG sin 20, okay, and this is FA. So, first sigma Fy equal to 0, the same exercise, Na is equal to MAG cos 20, then find out the downward force. The downward force here is MAG sin 20, you write MA 60 into 10 into sin 20 is coming up around 205 newtons. Then find out the frictional resistance which is given as mu s into Na, and that is mu s into MAG cos 20, and this comes around 232 newtons. So, here again your FC is greater than your downward force. That means, your FA is greater than downward force. That means body A will not slide. Will not slide. Now, the next aspect is about C. Now, the similar exercise has to be done for body B. This is body B, MB, G, NB, and you resolve this MBG sin 20, MBG cos 20, right. Now, if you calculate in this particular force, the downward force happens to be 136 newtons for this value, and frictional force happens to be around 112 newtons. That means, which is something different from the above two. That is, FB is less than your downward force. So, that means the frictional resistance offered here is less compared to the downward force component. So, in that case, B has to slide down because it does not have sufficient limiting friction. However, in this case, there is a great resistance by A on body B. Since there is a great resistance by A on body B, the body B does not slide. If there is no body A here, definitely the body B will slide because it cannot afford more frictional resistance. So, in a nutshell, you can say that all three bodies are held on the inclined plane without sliding. Now, let us move to the problem number 4. It's quite interesting problem. A cylinder of weight W is placed on a V block, and the cylinder surface touches the V block on both sides. Now, how much force P is required to pull the straight cylinder from the V block? So, this is the front view, this is a V block, and this is a straight cylinder. W is the weight of the block, and you are trying to pull the block from the V block. Now, you look at the side view. This is a V block of having an included angle 2 alpha, and W is representing the weight of the straight cylinder resting on V block. Now, to solve this problem, it is important to visualize the problem as a whole. Now, let me draw the complete picture of this V block. Right, and the cylinder is resting on this V block whose weight is W. So, these are the contact points. This is alpha and this is alpha because the included angle is 2 alpha. Then the force is applied in this direction to move the cylinder outwards. Now, when you notice the contact points, since the external force is acting outwards this direction, the frictional force at the contact surfaces will act in opposite direction. Let me call F. Then the cylinder having in touch with the edges of the V block will create reaction forces N. So, because N is the normal reaction exerted by the V block onto the cylinder on both sides. So, let me call this as alpha, similarly this also alpha. That means, if I resolve this normal reaction, this becomes N cos alpha and this becomes N sin alpha, and this becomes again N cos alpha and N sin alpha. So, let me draw the free body diagram from this point of view. So, if you have the cylinder and this is the weight, then the normal reaction is 2n sin alpha, because you have two vertical resolved components of the reactions, 2n sin alpha. Then you have two frictional forces along the length of the cylinder. When P is acting this way, the frictional resistance, that is 2F, acts in this way. Now, let us calculate the value of P, which is of our interest. Sigma Fx equal to 0, P is equal to 2 into F, that is 2 into mu into N. Now, sigma Fy equal to 0 gives us W equal to 2n sin alpha, or N equal to W by 2 sin alpha. Now, substitute, let us call this as equation 1, equation 2, substitute to N in equation 1, that gives us P is equal to 2 into mu into W by 2 sin alpha, where P is given as mu W by sin alpha. So, the amount of force that is required to move the cylinder from V block depends upon the coefficient of friction, the weight of the straight cylinder, and the V angle, half of the V angle. So, these are the parameters that influence the motion of straight cylinder from the V block.